Okay, last lesson in the unit on forces is forces on an inclined surface. So the goal today is I can draw a correct free body diagram for an object on an inclined plane and complete the required calculations for the applied forces. So usually with this, it's far more important. We do stuff with this in grade 12. The problem I find is people who take the grade 11 course struggle with finding the forces on the inclined plane and therefore struggle with the grade 12 concept. So all I'm doing here is adding a lesson into the grade 11 course, which falls under free body diagrams. It fits in perfect, but you just practice calculating the forces on the inclined surface. Okay? Very important to be able to do. So I want to go through the geometry quickly here with you in order to give you a feel for what the forces look like. So if you give yourself an inclined plane, and that inclined plane is at some angle theta, and we're going to put the box or whatever object we're going to put on the inclined plane. What I want to do is I want to look at the forces that are acting on it. So force due to gravity, Fg, is always pointing straight down. So I did extend it through the base for a reason. So there's my force due to gravity. My normal force, remember, normal force is always perpendicular to the surface. So there's where my normal force is. Now, what is pulling this object down the slope? So the force that's pulling anything that's on a slope surface wants to go down that surface. So we are going to have a force coming down here, and I'm going to call it, this particular force, the notation I use is FAX. Okay, and I'll explain the why here in a second. What's keeping this, or what's the normal force equal to? All right, that's one of the questions I want to address. What does the normal force equal? Because it can't be just force due to gravity. They're not in line anymore. All right, what I mean by not in line, the normal force and the force due to gravity are no longer in the same direction. Force due to gravity, though, we can break it into a vector that matches up with the normal right here. And I'm going to label this FGY. And actually, this should have been FGX. Okay? So there we go. The gravity vector actually gets broken into two components. And what I have done, and the reason I have X and Y, is because what I've done is I've taken basically an X-axis that would normally head this direction. I've rotated it theta degrees, so now my new x-axis is along here. And that's why I called this FGX, which would mean that this axis that got rotated would be my new y-axis. All right. So that being said, we just need to start breaking down the component, or breaking gravity into its components. So here's where the fun begins, our geometry. I know this angle here is theta. I know that the force due to gravity would make a right angle with that. So this angle up here would be 90 minus theta. Okay, that's how you'd find that unknown. Now, force due to gravity y is perpendicular to that surface, which means that it's 90 degrees, or perpendicular, 90 degrees. So this angle in here would be 90 degrees. I'm just going to do the calculation out here. 90 degrees minus the angle on the other side, which is the 90 minus theta. So when you do distributive law, you end up that this angle is theta. So the angle theta here is the same as the angle there, which makes the math a lot easier because this is the angle that's often given. So the question up here is what's the normal equal to? Well, using our vector notation, I give you the following values. Theta, if theta is given, so that's your inclined angle, then what do we know? Well, I know that the normal will be equal to the normal force, which is equal to FGY in this case, will equal the magnitude or the value of Fg cos theta, which is equal to, and you can break this down to its lowest base here, mass times gravity cos theta. So that's what your normal force would be equal to for an object that's on an inclined plane. So no force is acting on it other than the force due to gravity. Next year, or in the grade 12 course, we add in some extra values. So it's important that you can calculate the normal force. The other important force is that Fgx, the amount of force pulling it down the slope. And Fgx is, again, magnitude of your force due to gravity, sine theta, or formula you can put on your cheat sheet here, mass times gravity, that's Fg sine theta. All right, so there we go. That would allow you to calculate all the information you need given with an object on the slope. So you don't have to reproduce this. I'm just showing you where it came from and that you have the skills. It's just grade 9 geometry, finding that angle and then taking your vector knowledge to find those components. Look at an example here. Determine all unknowns. So I got to give this an angle here. So let's just add an angle of, let's call that, looks like 30 degrees to me. And over here it tells us that the mass of the object is 40 kilograms and the object is stationary. So what is involved here? Well, you will always have a force due to gravity, which would mean that your other two will have an Fgx and an Fgy. Now, you'll have the objects not flying off the slope, so you need a normal force. And if the object's stationary, that means that there must be a frictional force. So there's my free body diagram. There are 1, 2, 3, 4, 5 forces we need to calculate. So we start with force due to gravity. And that's just mass times gravity. 40 kilogram object multiplied by 9.81 gets us something a little less than 400. So 40 times the 9.81, 392.4 newtons. And because I have the diagram there, I'm not going to worry about playing with the directions here. So now, once I have Fg, I can get Fgx using your formula sheet or the formula we derived back here. It's just going to be mg sine theta. Mg sine theta. So 40, 9.81 sine 30. So 40 times the 9.81 times the 30 sine gives me 196.2. So that's the amount of force pulling the object down the slope. Now, if the object's stationary, that would mean that in this case, it's also equal to my force due to friction. So I've answered, I've got Fgx and Ff in one calculation. Similarly, my normal force, because there's no external force, is going to equal Fgy. So I'm going to be calculating those two values at the same time as well, which is mg cos theta. So like I said, there's no tricks to this. If you're looking at this thinking, well, I'm just calculating using these formulas, it's exactly what you're doing. Because remember, I just want you to be able to find these vectors. And like I said, people in the grade 12 course struggle finding these values. So what I do is I give you an advantage here. So that's 340 newtons. I give you an advantage in the grade 11 course. We just do the free body diagram. And next in the grade 12 course, this you'll be far more comfortable and we can start throwing the grade 12 material or twists at you. Okay? I have one last example. Didn't draw in my angles. I wish I would have done that. So let's go down and let's say this is 20 degrees. We have our mass. It's 50 kilograms. And this time we have an acceleration. So first thing we do is we want to draw in all our vectors. So force due to gravity, Fgy, Fgx, F normal, and force due to friction. So we start with our force due to gravity because most of our formulas stem from that, and that's mass times gravity. So 50 times 9.81. So times 9.81, oops, we get 490.5 newtons. So there's your FG. FGY is equal to my normal force, so the only two in that direction. So I'm going to get both of them in this calculation. So that's your mg cos theta. So we have our 50 times 9.81 cos 20. So 50 times the 9.81 again times the 20 cos. And I get 460.9 newtons. And then the FAX is going to equal, and it's not equal to force due to friction this time because of this acceleration. All right. So please don't always assume it's equal. So 50, 9.81 sine theta, so sine 20 equals, so 50 times 9.81 times 20 sine. So I get 167.8 newtons. All right, so now we need to find, we're finding all unknowns, so I need to know my force due to friction. So how do we calculate that? Well, we know that unbalanced force, Fu, is equal to mass times acceleration. We know that unbalanced force would be our applied or driving force, FAX, minus force opposing motion, so force due to friction, equals ma. Once we do that, we find out, I know what FAX is. It's the 167.8 minus, here's my force due to friction. Mass of the object is 50, acceleration is 0.2. So we find out we only have one unknown here. So we have 167.8 minus the force due to friction, and 50 times the 0.2 is 10. So rearranging, we find our force due to friction is equal to 157.8 newtons. Okay? That's all I want you to do. All you're doing is calculating those 5 vectors I have drawn on there. You're going to have the same 5 vectors when it comes to the homework and to the test, the exam, and it's just practicing exactly that. Can you calculate those values? Because the grade 12 course, it's necessary. It's going to be assumed knowledge. Hey, you can calculate this. I don't have to review that. This is the last component of this unit. The review is going to be posted there on the website. Once you're ready to move into that, please do, and we can set a test date. Good luck on the test, and we'll see you in the next unit.